All right, welcome back to the Blood Gas of the Week. This is case number 2. Again, we're going to jump straight into interpretation, so if you need a refresher on the normal values or how to interpret blood gases, go check out the how-to videos first, then come back to this video. If you haven't already, look at the case scenario above and then write down your blood gas analysis, then come back to the video. All right, here we go. This is an 11-year-old male castrated German Shorthair pointer with a 6-hour history of acute onset vomiting and diarrhea. The diarrhea is profuse and has become bloody, prompting presentation to the emergency room. On presentation, the dog's ambulatory, but he's really quiet. His heart rate's a little high. His mucous membranes are bright red. Capillary refill time is nearly instant. And his blood pressure is a little bit low at 95/50 with a mean of 68. His blood work looks like this. And the first step in our blood gas analysis is to determine if this is an arterial sample or a venous sample. This one's venous, so we're going to go ahead and go straight on over to the acid-base analysis. The first step is to look at the pH, which is a little bit low at 7.21. So this is an acidemia. We said acidemia can be caused by either a high PCO2 or a low bicarbonate. Our patient has a low PCO2, so that's not the problem. His problem is a low bicarbonate, which means his primary problem is a metabolic acidosis. We would expect to see a respiratory alkalosis as compensation, which is a low PCO2, and indeed, that is what we see. Okay, if you prefer the tic-tac-toe method, we see that his pH is a little bit low, which is an acidemia. The CO2 is low, which means we have a respiratory alkalosis, and the bicarbonate is low, which means there's a metabolic acidosis. So, we see which process lines up with the pH. In this case, it's the bicarbonate. So the metabolic component is causing the primary disturbance. Our patient has a metabolic acidosis. The PCO2 is moving in the opposite direction, a respiratory alkalosis, so this is probably his compensation. Our patient probably has a compensated metabolic acidosis. Now, you can stop here if you wanted to, but if you want to be certain what's happening, then we move on to the next step, where we calculate the expected amount of compensation. Since some of our really sick patients can have more than one problem that can cause changes in the blood gas, we can use mathematic formulas to determine if the changes that look like compensation really are compensation, or if we need to go looking for secondary problems. When the primary problem is a metabolic acidosis, the formula says for every 1 point decrease in the bicarbonate below normal, the PCO2 should decrease by 0.7 points. So, let's look at our patient. Step 1 is to see how much the bicarb has changed from normal. So, normal bicarbonate is about 20. We're going to subtract our patient's bicarbonate of 11.3 from the normal bicarb of 20, and that gives us 8.7. So, for every 1 point change in the bicarbonate, the CO2 should change by 0.7 points. We're going to multiply the 8.7 times 0.7, which gives us 6. So we think the CO2 should go down by about 6 points in response to the abnormal bicarbonate. The normal PCO2 is about 40, so we subtract 6 from 40, and we get 34. This means we'd expect the CO2 to be about 34 if the change in the CO2 is just compensation for the metabolic acidosis. But we know there's a range of normal CO2 and a range of normal bicarbonate for all of our patients. So in order to account for that, we're going to put plus or minus 4 on either side of our calculated number. So 34 minus 4 is 30. 34 plus 4 is 38. So if our patient's PCO2 falls into this range, we're going to say that he has compensation for his metabolic acidosis. And indeed, at 31, our patient does have a compensated metabolic acidosis. All right, so that is our final diagnosis today, a compensated metabolic acidosis. Thanks for checking out the video. We'll do this again next week. Until then, keep the rubber on the road and the blood inside.